Hello! Our video today is about ideal traffic assignment. We'll delve deeper into the application of ideal flow for traffic networks, see how to calculate ideal flow from capacity matrices, and see how to use this information to determine speed, travel time, and delay. This video is part of a series of tutorials on research output in graph theory related to transportation science. We'll pick up where we left off last time in our video about stochastic matrices and the Excel add-in. It's recommended that you watch the last video if you haven't yet. In the last video, we used the stochastic matrix to compute for ideal flow. Rather than depending solely on network structure by using an adjacency matrix, we used the stochastic matrix. We used probabilities to compute for ideal flow. In this video, we discuss the capacity matrix, and from there we'll jump on to using these matrices and the ideal flow that these generate for ideal traffic assignment. Let's start with an obvious first question. What is a capacity matrix? It's another square matrix, but this time, instead of denoting the presence of network links with ones, or denoting the probabilities that agents will pass through the links with, we denote the capacity of the road. For capacity matrices, we don't have to have data on probabilities like we did for the stochastic matrix. Of course, it would allow us to calibrate our model better, but for now, all we need are capacities. There are many different ways to measure the capacity of a certain road. We could measure it through the number of lanes in that road, or the road width. Capacity represents the maximum number of vehicles that pass through the road. While we could obtain this through empirical data, we could also make a general assumption. According to the Highway Capacity Manual, or HCM, approximately 1,500 to 2,000 passenger car units, or PCU, travel through a single highway lane per hour. A car is equivalent to a single PCU, a truck or a bus is 3.5, a motorcycle 0.5, so on. So we can also measure capacity in PCU per lane per hour. Since we're going to assume all the lanes are the same width, the capacity of each lane would be the same for all roads. It would be true to say that not all roads are of the same width. Highways will be larger than rural back roads and will transport a different number of vehicles. And so one could instead measure capacity using road width. In that case, it would be more complex, and you would have to assign a certain amount to a road width as the function of road capacity. For our simplified sample road, we know the number of lanes in each road, as given here. From here, we can transform capacity as the number of lanes into a stochastic matrix. The probability of going through a road can be assumed as the capacity of that road over the capacity of all the roads that lead out of the node they come from. This would be 3 over 4, this 1 over 4. Since this is the only road, this would be 3 over 3. We can do that for the rest, and then let's fill in the zeros. From this stochastic matrix, we can determine the ideal flow. While there is merit in showing this additional step of creating a stochastic matrix, with the add-in, you could also compute the ideal flow directly from just the capacity matrix. Now that we have our ideal flow, we can convert our capacities into PCUs per road per hour so that we can create a better example. Now that we have the capacity of the road and the ideal flow, we can get the congestion of the road. You can see that this road has the highest ideal flow despite only having 3 lanes. It's actually congested. These roads here, with 4 and 5 lanes, should ideally have fewer lanes. While this is useful as well, it's still only the bare bones of what we can do with traffic assignment. What if we had real-world data? How do we calibrate our results to adjust to this data? We actually only need one flow data from the road with the largest flow over capacity ratio. The computation of ideal flow would help us identify which particular road we need to survey, which is this road because it has the highest flow over capacity ratio. Let's say we found out from our survey data that 5,700 vehicles pass through this road per hour, Because we're assuming that our network is strongly connected, from this piece of information you can get the numbers for all the other roads. Let's do this. Go to Settings, Scaling. What we want to do is set it so that the flow through this road is 5,700. We know that this is the largest flow, or the maximum flow, so all we have to do is set max flow to 5,700. It will automatically calibrate the flow for us. There, now we have about 5,700. So we've now scaled the flow for the rest of the roads. From this, if we divide the flow and the actual capacity of the roads, we'll be able to get congestion of the roads. What else can we do with this data? We can get performance indices such as speed, travel time, and delay. This is the formula for the average speed matrix. This U here refers to maximum speed. This W is the flow over capacity ratio, which represents the level of congestion. We already have the flow over capacity ratio for each road. The only thing we need now is the maximum speed. The maximum speed represents the free flow speed. This is the fastest speed a vehicle could go through a certain length of road if there were no congestion and there was free flow through the road. We could also use speed limits if there were speed limits set on the road. Free flow speed can be measured empirically, or it can be estimated through a formula provided by the HCM, which starts with 70 kilometers per hour and has adjustments for the lane width, number of lanes, interchange density, and right shoulder lateral clearance. We'll assume everything but the number of the lanes is same. So these are their free flow speeds. Let's use the formula. This is the speed in kilometers per hour for our roads under ideal flow. Now that we have speed, what if we want to know how long it takes to traverse through the road? You'll notice that the formula of travel time is the length of the road over the speed that we already calculated. Real-world data would require the measurement of roads or the use of scaled maps such as Google Maps. We'll assume all our roads are the same length. Let's say 4 kilometers. Now we can compute for travel time. There. Let's multiply it by 60 so we can see it better in minutes. Now we have a matrix of the travel times through the road. Finally, we want to get the delay, which is just the difference between the travel time of the current flow and the travel time of the free flow speed. Let's calculate it here. And here are the results, also in minutes. This is the delay that cars have in passing through each road. We already knew that this road was more congested than the others, but now we have a tangible number to visualize this congestion with. To recap, we started by introducing the capacity matrix, and from there showed how to transform it into a stochastic matrix, and how to use these matrices to obtain the ideal flow. With the ideal flow, we were able to obtain congestion levels in terms of the flow over capacity ratio. Using scaling properties of ideal flow, we calibrated the congestion level using real-world data. We were then able to look at how to determine speed, travel time, and delay in our road network. Using ideal flow to simulate road networks and determine ideal traffic assignment is simple, especially with the ideal flow add-in, and requires much less data than traditional traffic assignment methods.
I hope you enjoyed this video tutorial. You can also visit other tutorials from Dr. Cardi's website, people.rivaledu.com/Cardi, and the Ateneo Pedestrian and Traffic Computing Laboratory, pinoy.admu.edu.ph/-FedLab. Thank you for watching.